like no direct connections between Wuppertal and Bochum. It's just 20 kilometers or so. But by train, you have to go via Düsseldorf or via Dortmund, very complicated things. So actually, I always have to rely on my car.
Oh, so you always take the car?
I always take the car.
Okay.
I mean, there's a direct bus connection, which takes almost 1.5 hours. By car, it's like 20 minutes or so.
Of course.
It's spooky here being in this empty building. I mean, it's almost empty. I can hear some people talking somewhere on the floor. But yeah.
Wow. And so you say that's the first time since March, basically, that you're there?
Well, almost. Yeah, almost. I have been here a few times, well, 2 or 3 times only. When Hans Franzen defended his habilitation thesis, then that was actually in a lecture hall with 20 people allowed to be present and all the rest via Zoom. And of course, then I really wanted to attend, and that was when I was here. But I haven't really worked in my office since March. Yes.
Yeah. And interesting. And I mean, we haven't been back since March, and I don't. I mean, we can sort of go and collect stuff if we register beforehand, but that's about it.
Yeah.
And of course, Leicester is the COVID hotspot of the UK. So but, I mean, the mind-blowing thing is that it comes from these illegal sort of low-paid textile factories, like sweatshops, basically.
Okay.
There are 1,500 in the city. Unbelievable. More than inhabitants, but no. and the point is they're still open, so they know that that's where it comes from. They know that they sort of pay people maybe £3 an hour, and they live in, work in terrible conditions. But it's like a banana republic. It's unbelievable. I mean,
but they're still open, and then okay.
I actually saw that on the news. I think they'd done a broadcast about that, and they were trying to interview the managers, but only one person would talk to Sky News, I think.
Surprising.
Wow.
It's a bit like the meat factories in Germany, right? Where you have these
exactly
work conditions, and now it comes out. It should have come out much earlier, but
definitely, yeah. There was this massive 1,500 infections in this meat factory, and it was closed for a few weeks. It opened again today.
Oh,
but
really?
Of course, but the whole of Germany is now watching really, really closely what's going on there.
Absolutely, and I think somehow the conditions of that meat factory are probably the winter condition in the UK.
Actually, at least Leicester made it now in the New York Times. They had an article. There was the word Leicester and the word plague next to each other. We are quite worried because we have to worry about students' numbers, because they basically relate directly to our income.
Yeah, sure.
We have to make sure that they will come, or at least come virtually, or and that's really tough.
Something.
Wow.
Liam, shall we briefly have a quick word about the housekeeping? So I think we can just probably skip the housekeeping slides by now, because
okay.
So can you just briefly run me through the rest of the introduction slides?
Yeah, so I have screen share. Why won't it not? There we go. I was just deleting the housekeeping slides. Screen one.
Okay, great.
Oh, my Zoom's vanished.
So it went through the cow list today.
Cool, great.
So slide one. I just have that as the holding slide for when people.
So this is the holding slide, okay?
Yeah, just for when people are entering the call. I've removed the housekeeping.
Okay.
And just to advertise next week's seminar.
Yeah.
And then today's speaker.
Live screen.
Okay, perfect.
We will live screen it on YouTube. Marcus, I hope that's okay. I can't hear you.
Oh, your sound has disappeared, Marcus.
No, you're muted.
Just realized.
I just want to say that we put a live link also on YouTube, because there are always people who want to watch it over researchseminars.org, so they can see it online.
Whatever.
Okay.
That's fine.
I should ask your permission because otherwise.
Yeah, sure. Yeah. No, but
we have permission to record as well, so that's great. I'll record as soon as you start to.
Perfect.
I actually have a quick question. So where's it gone? After this seminar, oh no, we've got next week, the 23rd, and then after that, we're having a gap until the 27th of August. Is that correct?
That's right. And then we start again on the 27th of August. Oh, I've actually been thinking today whether we should move that seminar and start the week after. But I think Frank and I will decide that this week, and then we'll let you know.
I think we also need some holidays at some point.
Yeah, you definitely do.
Oh, Marcus, we are in your email. Sorry. Okay.
Yeah. Right. Thanks.
Okay.
Yeah, no.
I just thought you might want to know in case everybody comes
I
in.
just realized. Okay, now it looks better. Yeah.
Okay.
Yeah. Okay. Yeah, that's good.
Actually, my connection was broken for a minute or so, and so I had to restart everything. But now.
Oh, okay. Yeah. Okay. Well, if that happens, we'll just wait. Not to worry.
It's really great that you accepted our invitation. We're very happy for that.
Yes. Thanks a lot. Would of course been great to be at Leicester, but at least we have this very important
maybe
chat and
Exactly.
So
what we'll be missing is the dinner after the talk.
Yeah, that's right. Exactly. Yeah, and also, I mean, it's kind of nice to sort of be able to sort of have a longer informal discussion.
We can definitely do about the dinner at some other point when we are all allowed to travel. Maybe you would like to come and give a real talk here in Leicester. LMS talk.
Oh, okay. So it's my connection that's gone bad.
Okay.
Okay, I'm just going to admit everyone into the call now. Marcus, I will share my screen just for a couple of minutes, just for the start of the call.
Yeah, sure.
Okay, I'm briefly going to disconnect and reconnect.
Okay.
If you let in, Liam, if you let in everybody, that's fine. I think it's 1 o'clock now.
Oh.
Yeah. Oh.
No.
The room's filling up now.
Wow.
Excellent.
Okay.
Looks like we get quite a few people now. Okay.
Yeah, it's filling up nicely. We're just letting everyone connect.
Good to see so many people. Great.
Yeah.
Thanks for joining, everybody.
Do you just want to open up the waiting room and disable it, Liam?
Yep, that's it. It should be disabled now.
Okay.
Enable waiting room. Everyone should be able to just join freely now without having to be accepted. Yeah. Oops.
Okay, shall we start then? Okay, it's my pleasure to welcome you to this week's edition of the LAGOON Leicester Algebra and Geometry Open online seminar. Before introducing this week's speaker, Marcus Reinecke, let me announce next week's seminar, which will be the last seminar before we take a short break and then take up again in September. Details will be on the webpage and announced next week. So next week, our speaker is Laura Shaposnik from the University of Illinois at Chicago, and she's going to speak on speaking on generalized hyperpolygons. And okay, so now it's my pleasure to introduce today's speaker, Marcus Reinecke from the Universität Bochum in Germany, who is going to tell us about Fano quiver moduli.
Thank you very much for the introduction. Thanks for coming. I should share my screen.
Yes.
Here we go. You can see the presentation.
Yes.
Yeah. Okay, so thanks a lot. That's actually my first research talk since, well, you know what, and it feels great to do it again, at least online. And I'll talk about a recent preprint joined with Hans Franzen and Silvia Sabatini which is also on the archive. And it's not a big and deep result, but it somehow fits very well, I think, to the topics of the seminar, and also gives me the opportunity to somehow recall some of the basics of moduli spaces and stabilities. And so I thought it's somewhat the right topic for the seminar. And so let me show you what the aim is, if I manage to. Okay, so the aim of this talk is to exhibit large classes of moduli spaces of stable quiver representations, which I will introduce again, which are smooth projective Fano varieties. And well, as I said, it's not a very deep result. It was also somehow almost discovered before, but it's hopefully a start of something, as we will see. So the plan for this talk is part one. I will just recall what are these quiver moduli spaces I will talk about. Part two will be into stabilities, and this will be old-fashioned Mumford stabilities and nothing fancy, Bridgeland, whatever. In part three, I will explain the main result and give you a sketch of the proof. And part four will be about examples. And for me, the examples are actually the main interesting and difficult point, but I will skip all the difficulties for this talk. All right, so let's start with definitions. And first we need some standard quiver notation. So all the time Q will be an acyclic finite quiver, and you should always think about a wild quiver, because all this theory of moduli space is not interesting if the quiver is of Dynkin or extended Dynkin type. All you get for Dynkin or extended Dynkin types are empty moduli spaces, single points, or a P1 projective line. So that's not so interesting from the point of view of algebraic geometry. So think about a wild quiver. All right. The set of vertices of the quiver I will always denote by Q0. The arrows are always written as alpha from I to j. Associated to the quiver, we have the homological Euler form. And we also fix the dimension vector d all the time. And last datum, we will fix a stability. And stability for me at the moment is a real valued linear function on the set of dimension vectors, which evaluates to 0 on the given dimension vector d. Actually, instead of the reals, you could just take integers or rationals. Talking about stability space later, that's the reason why I want to include the reals, but that's not the main point, as you will see later. Okay, so this is our dating. We have a quiver, the dimension vector, and such a linear function which evaluates to 0 on this given dimension vector. Now comes the central definition of stable representation. So a representation V of this given quiver Q of dimension vector D is called theta stable if theta evaluates to something less than 0 for all non-zero proper subrepresentations of V. Yeah, so you take all the subrepresentations of V, you record all the dimension vectors of the subrepresentations, plug them into the stability theta, and that should be less than 0. That's a stable representation, and it's really the notion of stability which was also appeared in the theory of vector bundles. Beware, this is contrary to Alistair King's convention, because Alistair King always wants to evaluate theta to something bigger than 0 for stable representation. I follow some of the vector bundle convention to have it evaluated to something smaller than 0. But that's the only difference, and it's just a sign change which you can ignore for this talk. Okay, so here's the main result of Alistair King. Under this hypothesis, there always exists a complex algebraic variety parameterizing the isomorphism classes of the stable representations of this fixed dimension vector D. Okay, so that's the moduli space. The idea of this is that, well, if you have a wild quiver, you have a wealth of representations, and your representations appear in continuous families, and you want to understand these continuous parameters on which the representations depend. And that's why you want to do moduli spaces. Yeah, so it's a space, complex algebraic variety, encoding all the continuous the continuous parameterizations of your representations. And that's what it's good for. Okay, so properties of these. So here's the theorem again. Now I will tell you some facts about these varieties under a certain hypothesis, which somehow shows a bit where they are placed in algebraic geometry. So let's make the following assumption, which is essential, and I will illustrate it later with a few pictures. In the theory of moduli spaces of vector bundles, there's always a coprimality hypothesis. It's always that rank and degree of vector bundles should be coprime. We make a similar coprimality assumption here. So we always make the assumption that D is theta coprime, which means that theta does not evaluate to 0 for all the potential subrepresentation vectors. So all potential dimension vectors of subrepresentation. And the question is, how restrictive is this assumption? We'll discuss this later when we discuss stabilities in general. If you make this assumption, then there's no difference between stability and semi-stability. I haven't told you what semi-stability is actually, because we don't need it. But if you know the story, this assumption tells you there's no difference between stability and semi-stability, and that makes life much nicer. Facts. So first of all, if this moduli space encoding all the continuous parameterizations, if it is non-empty at all, so if there is stable representation at all, you automatically get an irreducible smooth projective variety, and the dimension of it is 1 minus Euler form dd. And this dimension parameter actually shows you that this is not interesting if your quiver is not wild. Yeah? So if your quiver is of Dynkin type, then the Euler form is positive definite. So the minimal value for dd is 1. So you can only get 0-dimensional moduli spaces. And a 0-dimensional irreducible variety is just a single point. If you have an extended Dynkin quiver, then the Euler form is positive semi-definite. So the Euler form dd can only evaluate to 0. So you get a 1-dimensional irreducible smooth projective variety. So smooth projective curve. So only curves can appear. Let me show you the next fact. Due to Schofield, that these moduli spaces in this coprime case are always rational. And that solves already the 1-dimensional case. If the Euler form dd equals 0, then you have a 1-dimensional smooth projective variety, which is rational. So it's automatically a P1 projective line. Yeah. And this shows us that for Dynkin and extended Dynkin quivers, no interesting moduli spaces appear. You just get empty or single point or projective line. Okay, so that's the reason why you should think of a pretty wide quiver cube. And then, of course, you can have moduli spaces of arbitrarily large dimension, because if your quiver is wild, then the Euler form is indefinite, and you can have dimension vectors such that 1 minus dd is arbitrarily large. Yeah? So you get moduli spaces of arbitrarily large dimension. And it also shows you that the dimension somehow grows quadratically. Yeah? So think of this d growing, then Euler form dd, this being a quadratic form, should somehow grow quadratically. So the dimension somehow grows quadratically when you make a linear change in the dimension vector d. So these varieties are of very large dimension. But they're always irreducible, smooth projective, and rational. Rational is already a quite severe restriction. Topologically, we know a lot about these moduli spaces, about their cohomology. So King and Walter showed in the mid-90s that they always have algebraic cohomology. This means the odd Betti numbers all vanish, and all the even cohomology is algebraic in the sense that the cycle map from the Chow ring to the cohomology ring is an isomorphism when going to the rationals. Yeah? So the only cohomology is algebraic. That's also a big restriction for these moduli spaces, somehow in the classification, in the putting them in a place in algebraic geometry. These are qualitative results. There are also quantitative results, which I don't want to discuss today, but just mention. Actually, there is an explicit formula for the Betti numbers of these moduli spaces, somehow resembling the Adenauer-Simon formula for the Betti numbers of moduli spaces of vector bundles on curves. And there are even explicit generators and relations for the cohomology ring structure. That's the result due to Hans Franzen. Yeah, so we know a lot about topological properties of these spaces. Another question is, where are they somehow placed in the classification of algebraic varieties? And that's our topic today. And we want to see when they are placed in the Fano corner of algebraic varieties. Yeah, so these are a lot of facts, but just shows that well, at least we know quite a lot about the topology of these spaces. So I briefly want to tell you something about the construction of these moduli spaces. If you see all these moduli spaces for the first time, then maybe you don't want to know the details of the construction, but I will just explain the bare minimum of this without referring too much to Mumford's geometric invariant theory, because it's interesting for the sketch of the proof later. So let me do this very roughly. So first of all, without loss of generality, this I will explain later, we can always assume the theta to be integer valued, our stability function, and not real valued. Let's assume this for a minute. We fix vector spaces vi of dimension di. Well, that's part of the datum of a quiver representation. If you want to have a quiver representation of dimension vector d, you first fix the vector spaces vi, and then you fix the linear maps on the arrows. Okay, so let's first fix the complex vector spaces, and let's consider the standard base change action. The space Rd, that's the space encoding all the linear maps you can write on the arrows, right? So given the quiver representation on these vector spaces vi means you have to choose a linear map for each arrow in the quiver. And on this, you have a base change action by the product of the general linear groups of the vector spaces involved. And that's this standard base change action gi acts on v alpha by gj, v alpha, gi inverse. And by definition, by the very definition of what a quiver representation is, the orbits for this action are precisely the isomorphism classes of quiver representations of this given dimension vector. So that's the very first step in a geometric approach to quiver representations. All right, so now to something complicated. Okay, so let's digest this definition. I would like to define a ring. So this will be called the graded ring of semi-invariance of weight theta. So, and this is a ring consisting of polynomial functions on Rd. Well, this is something quite easy at the moment, because Rd, as you see here, it's just a huge vector space, and we are just looking at polynomial functions on this vector space. So just polynomials in the entries of matrices representing these linear maps. And these polynomial maps should have a certain transformation behavior. They should almost be invariant functions. So if you look at this line, f of g times v should be almost f of v for all g and v, except for some strange expression, which, if you look at it, it's just a scalar. Yeah? This is just a scalar, just the product over all vertices, determinant of the operator gi to a certain power involving the theta. So this means your polynomial function f should almost be an invariant. It's a semi-invariant. If you translate v by g, you get the same value of f except for some scalar depending on your stability theta. So this is called the graded ring of semi-invariance of weight theta. By Hilbert's theorem, this is a finitely generated graded ring because GD is a reductive linear algebraic group. Aha, so it's finitely generated, so we can choose finitely many generators. So and we can attach to it a projective variety. So just go back. So here we have this graded ring of almost invariant functions on quiver representations. And now we define the moduli space of stables just as the approach of this graded ring. I would like to be a bit more suggestive because that's some of the point which I will make in the sketch of the proof of the main theorem. So what does it mean to take the approach? It almost means the following. Choose homogeneous generators of this ring. So it's finitely generated, so we can choose homogeneous generators, and without loss of generality, let's say they're of the same degree. That's not literally true. You can't always find homogeneous generators of the same degree. Well, if they're not of the same degree, then multiply them several times so that they are of the same degree. So that's a bit sloppy, but it's fine for my purposes today. And then you do the following with these generators. You put these generators together and they define a map for you from RD, the set of all quiver representations, to a large enough projective space, yeah, by just putting all these together. And well, actually, it's dangerous to define a map to projective space given some polynomial functions, because it might happen that all the polynomials evaluate to 0 at the same time. And that's not a point in projective space. So that's why we restrict here to the stable locus. So to all points in this huge vector space, which correspond to a stable representation. And if you do it like that, then the following holds. So first of all, then this map is well defined. Meaning, if you take these generators for the ring of semi-invariants, they do not simultaneously evaluate to 0 on stable representations. So it's a well-defined map to projective space. Moreover, it's a closed embedding into projective space. And the image of this embedding we define as the moduli space. So that's a very down-to-earth, bit sloppy, but very down-to-earth definition of that moduli space. And that's actually what you do when you compute examples. Yeah. So in low dimensions, you actually work out what does it mean to be a semi-invariant function. Can I find generators for this ring? And then you write down this map, and the image is the moduli space. So that's how you really work in concrete low-dimensional examples. Okay, so that was our excursion to the moduli spaces. And now we come to the second part of the talk, which is about stabilities. So this is maybe not so strictly necessary for this topic of Fano-Kruger moduli, but I thought it's a big topic in your seminar, so I should somehow elaborate a bit on the stabilities. So this is just, as I said, there's no Richardson stabilities, just old-fashioned Mumford stability, but for these moduli spaces, that's fine. So let me first define what I mean by stability space. And by stability space, I just mean a real vector space. This is the space of all, well, linear functions on RQ0. So you just choose a real for every vertex in your quiver. That defines a linear function, and you take all the linear functions evaluated on D to 0. Yeah? So that's a hyperplane in RQ0. So the dimension of this real vector space is just number of vertices of the quiver minus 1. Yeah. And in particular, if I want to draw examples, then the best case is a 3-vertex quiver, because that stability space is a 2-dimensional real vector space, and that's something I can draw, and you will see an example in a few minutes. Okay, so that's stability space for me. Stability space has walls. Namely, you have one wall for each sub-dimension vector. So again, we run through all the possible dimension vectors of sub-representations. All E, which are component-wise less than or equal D, but not equal to D and not equal to 0. And for these, we consider all the stabilities evaluating to 0 on E. So that's clearly a hyperplane in stability space. And what we get in this way are finitely many hyperplanes. And so what we have is a wall and chamber structure. Yeah. So this real vector space is divided into several chambers by these finitely many walls. The formal definition is take stability space, omit all the walls, decompose into connected components, take the closures of the connected components, but well, we will see in the picture what it means, and then it's more clear. Okay, so with these definitions, we can just note that the notion of a stable representation, so which representations of dimension vector D are actually stable, it doesn't change along the interior of a particular chamber. And that's why on an earlier slide, I said that without loss of generality, we can assume theta to be integer valued, because, well, you can just perturb your theta a little bit until you hit an integer value inside your chamber. And another remark is that this coprimality assumption, which I made at the very beginning, it just means that your theta belongs to the interior of a chamber. Yeah, so that is a generic corresponding to this dimension. All right. Maybe I should first show you a picture. So, okay. And then I will go back to the text later. So these are typical pictures for stability space. So the quiver here is the quiver with 3 vertices and 2 arrows from left to the middle and 2 arrows from right to the middle. So an average wide quiver. And stability space is something 2-dimensional. And here you see this 2-dimensional stability space, and here you see the walls. So in this case, the dimension vector here is 1, 2, 2, and the relevant walls are theta 3 being 0, theta 2 being 0. This anti-diagonal here means theta 2 plus theta 3 is 0, and so on. So that's typical pictures of stability space, and you see how it is decomposed into several chambers. All right, let me go back to the main text, which is the illustration for what the stability space is. Okay, so that was last time. So we have the stability space with walls and chambers, and the notion of stable representation doesn't change along the interior of a chamber. And this coprimality assumption, which is essential for getting nice moduli space, just means the theta belongs to the interior of a chamber. All right. So, but what we don't know yet is when is a moduli space actually not empty. So that's the topic of this slide. When is the moduli space? Oops, sorry, moduli space actually non-empty? For this, I recall a result of Schofield, and I need a definition. What is a generic subrepresentation type? So we say that a dimension vector E generically embeds into D if V contains a subrepresentation of dimension vector E for V in a dense subset of RD. So loosely speaking, almost all representations of dimension vector D admit a subrepresentation of dimension vector E. That's a generic subrepresentation. And then it's easy to observe that the moduli space we're interested in is non-empty, so we're really talking about some non-trivial variety, if and only if your function theta evaluates to something negative for all these E, which are a generic subrepresentation type of D. So that's a numerical criterion for which stabilities actually give you a non-trivial moduli space. This criterion would be great if only we could say, when does this hold? When is E actually a generic subrepresentation vector? And for this, luckily, we have a recursive criterion using Schofield. E is a generic subrepresentation type of D, if and only if the Euler form E prime D minus E is greater or equal to 0 for all E prime being a generic subrepresentation type of E. So that's the most compact formulation of it, and it's still difficult to check, but at least it shows you something about the recursive nature. So if you want to decide when a moduli space is non-empty, you have to find all the generic subrepresentation types of D. And you can find all the generic subrepresentation types of D numerically if you already know all the generic subrepresentation types of E for all the smaller dimension vectors. So in principle, it's a recursive criterion, very difficult to use in practice. And actually in practice, the best method for deciding whether moduli space is non-empty is to somehow try to actually construct one stable representation by making generic choices. Yeah. So, but at least in theory, there exists a recursive criterion for deciding when these moduli spaces are actually non-zero. But in any concrete example, it might be hard to actually find out. Okay. So that was general remarks about the stability. Okay, let me get back to this picture. So here again, we see two dimension vectors for this quiver, 1 to 2, 1 to 1. And I already showed you stability space and all these chambers. And the shaded region, that's the chambers actually producing a non-trivial moduli space. So it's only, in general, it's only a small part of stability space giving you an interesting moduli space. I hope you can see the shading. So it's always just these two regions here to the northwest. That's how it looks like in this example. Okay, let me get back to another topic, the so-called canonical stability. What is the canonical stability? The canonical stability is the following linear function. Evaluate Euler form of D with whatever minus Euler form of whatever with D. So you take the anti-symmetrized Euler form for D. This gives you a linear function, and this is called the canonical stability for a certain reason, which I will tell you about in a minute. So first of all, just one more notation. If D is theta can coprime, then we call C-can the canonical chamber, so the chamber containing this canonical stability. So let me explain. So this canonical stability might or might not be in the interior of a chamber in stability space. If it is in the interior of a chamber, then this chamber we call the canonical chamber, because it's the chamber containing the canonical stability. But as you will see in the example, it's not necessary that this canonical stability is in the interior of a chamber. And that's actually a problem for our main result, because it only applies in this case where it is in the interior. All right, so why this strange stability function? So here's the theorem of Schofield. The moduli space of stable representations for the canonical stability is non-empty if and only if D is a sure root. And sure roots are quite well studied in representation theory of quivers, although for wide quivers it's still something complicated. But what does it mean? Well, it means there exists one representation V which has trivial endomorphism. This is really great because this is something you can almost do constructively. So if you want to construct an interesting moduli space, we are given a quiver and a dimension vector D, and we want to construct an interesting moduli space. What do? Well, you choose a representation for this dimension vector at random, as randomly as possible. And you could really just pick random numbers as matrix entries. And then check by hand that the endomorphism ring is trivial. That's much easier to check than stability, indecomposability, or whatever. I mean, computing the endomorphism ring, that's something you can really do, yeah, with your random representation. And if you're lucky and your random representation has trivial endomorphism ring, yeah, then you are lucky. Then you have proved that D is a sure root. And then as your stability, you can always just take this canonical stability, and you know this moduli space of stables is automatically non-empty. Yeah, that's a great way to find interesting moduli spaces. Okay, that's the canonical stability. And let me summarize now finally summarize everything in these pictures. So, which I've already shown you twice. So Q is our 3 vertex quiver. That's stability space for the dimension vectors 1, 2, 1 and 1, 2, 2. They are both sure rules. So they're interesting. In both cases, you can eliminate the variable θ1 depending on θ2 and θ3, and so stability space is shown in the coordinates θ2 and θ3. You see the chambers. So we have 1, 2, 3, 4, 5, 6, 7, 8 chambers for the smaller dimension vector and 10 chambers for the larger dimension vectors. In both cases, we have only 2 chambers where we get non-trivial moduli spaces. And there's one big difference. For this larger dimension vector, the canonical stability, here in this case, it's, let me check, it's 4 minus 6, 4. So it's placed here. Here, in this case, the canonical stability is in the interior of the chamber, whereas here, the canonical stability lies on the wall. Yeah, so both are sure rules, very nice, but there's a big structural difference in that here the canonical chamber is on a wall. And in the following, I can't say anything about these cases. And here it is in the interior of the chamber. And so that's the canonical chamber, this one here. These chambers are always polyhedral cones. And yeah, this is the canonical chamber. So that's a small and rather random example, but just a case where we can draw nice pictures. Okay, that was the part on stabilities. Main result. So before stating the main result, when is a quiver moduli space a Fano variety, let me just very briefly recall something about Fano varieties. Caveat, I'm absolutely no expert on Fano varieties, but just let me give you the bare minimum of information we need. So now for a second, let's just assume X is a smooth projective and complex algebraic variety. It is called Fano if omega x dual is ample. So that's the anti-canonical bundle. The anti-canonical bundle should be ample. That's the usual definition of Fano. So what does it mean? So first of all, what is the anti-canonical bundle? The anti-canonical bundle arises in the following way. Well, X is smooth projective, so let's take its tangent bundle, and let's take the maximal exterior power, so the determinant bundle of the tangent bundle. That's the line bundle, and that's called the anti-canonical bundle. And this anti-canonical bundle should be ample. What does this mean? It means if you take a large enough capital N, you take the nth twist of this determinant of the tangent bundle, and you find global sections of it, such that if you put these global sections together, you get an embedding of X into projective space. Yeah. So Fano means you can find an embedding of X into projective space with sections of a power of the determinant bundle of the tangent bundle. Okay, so far so nice and classical, but it also looks a bit technical. So why all this hype about Fano varieties when just this is the definition? So let me well, of course you might, I mean, the buzzword is now maybe just mirror symmetry whenever you have Fano variety, but I mean, the basic importance of Fanos is that for any fixed dimension, there are only finitely many deformation classes of Fanos of that dimension. Thus, they are in principle something classifiable. They have a certain finiteness property. In any fixed dimension, up to deformation, there are only finitely many types. So you could hope for some classification. But we know that even in dimension 3, the classification is something extremely hard and some more milestone in algebraic geometry to have this classification of Fano threefolds. Well, but at least it tells us Fanos somehow feel rigid and have finiteness properties, and they somehow feel classifiable. In contrast to some of the opposite end of the story, which would be varieties of general type. Okay, and so that's the reason why it is desirable to know I mean, if we want to know where in algebraic geometry are our moduli spaces of quiver representations placed, that would be interesting to know when are they placed in the Fano corner of algebraic geometry, where things have finiteness properties and where things might be classifiable. So that's maybe the motivation for trying to find out when moduli spaces of quiver representations are Fano. All right. Okay, so after all these preparations, I can now formulate the main result. Here we go. Here's the theorem. We have to assume that the dimension vector D is co-prime for the canonical stability. So that means in our picture of stability space, let me go back to this picture. Here we go. So it means the canonical stability should be in the interior of a chamber. So this example is fine. This example isn't, because here the canonical stability is on the wall. So that's the first assumption we have to make. The second assumption is now you take a stability theta, which is in the interior of this canonical chamber. Any theta. Could be real or integer valued. Doesn't matter. So now here's a very strange condition. For all decomposition of the dimension vector into E plus F, such that the slope, the theta evaluated to E is bigger than theta evaluated to F, the Euler form is less than or equal -2. That's a strange condition. It's technical. We call it numerical ample stability. You will see in a minute the reason for why we need this condition. So what it basically says, for those people knowing, it tells us that there are no codimension 1 components in the unstable locus. So there are no divisors in the unstable locus. And that's an important condition for finding out the Picard group of the moduli space. So, well, at the moment, it's just a technical condition, which is difficult to check, as we will see later, but it's just necessary for this for this theorem. Okay, so these are the conditions. Then conclusion is this moduli space of stable representations, which is a smooth projective variety, and because of this first assumption, it is Fano of the dimension 1 minus dd, and the Picard rank is just number of vertices minus 1. And so actually in the theory of Fano varieties, there are many, many more numerical invariants of Fanos which you want to know. There's one more invariant we know, which is called the index of a Fano. I've skipped this for the purpose of this talk, but let me say that there are many basic invariants of Fanos which we haven't yet computed in this quiver setup. So there's lots of things to do. But well, here are the two basic invariants: it's dimension and it's Picard. Okay, so this holds under the condition that the canonical stability is sufficiently generic. Theta is also sufficiently generic in the canonical chamber, and the strange condition called numerical ample stability. All right. About the proof. So let me give a one-page sketch of the proof. No, before the proof, let me say that this theorem is not absolutely new. So in the case of the dimension vector D being thin, so all the entries of D are 1, this was already known by work of Altmann and Hille. So the case where D is thin, where all the entries are 1, that's the toric case, because you get toric varieties, toric Fanos, and that was done by Altmann and Hille. Also, this theorem was more or less announced in a preprint by Giacomo Fay from 2009, but it never appeared, and we don't understand his proof, but at least it was announced in almost precisely this form. And also Lutz Hille told me that he knows this result since 2002, but it's not published. So it's not absolutely new, which is maybe not a surprise because it's not that deep. But well, anyway. So let me go to the proof, or sketch of the proof. So first of all, without loss of generality, I just assume that our stability is the canonical stability, because the stability doesn't change inside the interior of a chamber. Let me quickly define PGD as the GD. What was GD? That was the structure group for quiver representations, the structure group modulo the scalars. And well, you might skip this this page here if you're not interested in these in the details. So here's a chain of isomorphisms, which I don't want to explain in detail. The only point is that the numerical ample stability comes at this point. So stability space is, and this is easy, isomorphic to the PGD equivariant Picard group of the vector space of all representations made into a real vector space. So this isomorphism is trivial. So here we move to the PGD equivariant Picard group of the stable locus, and to have this isomorphism, we need this numerical ample stability. So if you have divisors in the unstable locus, then this isomorphism does no longer hold. The Picard group really changes, and that's why this is essential. Now, from the equivariant Picard group of the stable locus, we can pass to the Picard group of the moduli space, because, well, basically just because we have a geometric quotient. No? So here is the equivariant Picard group of the space on which we are acting, and here's the usual Picard group of the quotient. Okay, so what does this mean? So here we have the Picard group of the moduli space made into a real vector space. It's isomorphic to stability space. And under this isomorphism, the canonical stability translates into the anti-canonical class. The canonical stability here translates into the anti-canonical class, which is not too difficult to see. You have to make some Chern class calculations. You need a resolution of the anti-canonical bundle, but it's just one page of Chern class calculations, and then you're done. Then you have this correspondence. And okay, so that looks good. Canonical stability corresponds to the anti-canonical line bundle. And let's compare, let's look at global sections. So let's digest this for a second. So here I'm taking global sections of powers of the anti-canonical bundle on the moduli space, and I'm putting them all together. And this is isomorphic to precisely this ring of semi-invariants of this degree. Yeah? So a global section of the anti-canonical bundle is precisely a semi-invariant on semi-invariant polynomial function. And I just see this should be theta can here. Yeah. So the global sections of the powers of anti-canonical bundle are just precisely the semi-invariants which we are considering anyway. And now comes the conclusion of the proof. By definition, the generators on the right-hand side provide us an embedding into projective space. Yeah, that's how the moduli space was actually defined. That's what I explained to you on this construction slide. You have this ring of semi-invariants. You just take homogeneous generators of the same degree. They define an embedding to projective space. Now, these generators of the ring of semi-invariants now translate into global sections of the anti-canonical bundle, and they provide an embedding to projective space. And that was precisely our definition of Fano. Let me go back to the definition of Fano. The definition of Fano is you twist the anti-canonical bundle long enough and you find global sections which provide a close embedding into projective space. And that's now precisely what we did by translating these global sections into the semi-invariants of precisely the weight we are looking for. Okay. And that ends the proof. So it's not terribly difficult, just these identifications of Picard groups and a certain Chern class calculation. And that's it. Examples. So all the work is in the examples, actually. Yeah, so the theorem is quite general. Let me show you the theorem again. So what do you have to do to work with this theorem? Well, you are given a quiver and a dimension vector, and you just first check whether D is co-prime for the canonical stability. Yeah, just place your canonical stability in stability space and look if you are on a wall or not. So that's easy to check. This condition, numerical ample stability, that's the hard condition to check. But once you have checked this, then you are done. You have found a class of Fanos. So back to the examples. An observation is that for any given quiver Q, this numerical ample stability, this technical property, seems to hold for almost all D. But verifying it in any particular case is quite non-trivial. So that was quite a frustrating story for me. So I first did some easy examples, and I will just present you the easy examples, and then I tried some more difficult examples, like this 3-vertex quiver, which I have shown as a running example. For these 3-vertex quiver, I had no idea when is this numerical ample stability verified. So I just made a computer experiment, and the computer experiment, the computer said, well, if D has entries up to 20, it's always valid, it's always fulfilled. Okay, so if it's always fulfilled, wonderful, then I should find a proof. But this turned out to be really, really hard, and I used 2 months and quite strange methods. Actually, I had to use a bit of analytic methods to actually prove this for this one single quiver. Anyway, so let me just formulate this as a slogan. Applying this main theorem requires us to verify numerical ample stability, but verifying it in any particular case is quite non-trivial, unfortunately. And I cannot tell you anything about the details, but maybe if you see this for the first time, they're not so interesting. By the way, I'm talking about this Fano thing, about this Fano paper for the first time. And talking about a paper for the first time, you always make the mistake of trying to convince the audience of this one technical lemma, which you have worked on for several months. And it's always impossible. And in this case, so the interesting part, which I'm really proud of, is verifying this numerical ample stability, but I cannot tell you about it. So let me just skip it. Okay, examples. The first class of wild curves we look at is Kronecker curve, generalized Kronecker curves. So just a 2-vertex quiver, ij, and m arrows from I to j. That's it. So here's the theorem. Assume that the quiver is wide, so n is at least 3, and assume that D and E, the 2 entries in the dimension vector, are co-prime. And then we consider this moduli space for the canonical stability, and assuming it is non-empty, is automatically Fano of dimension m times D times E minus E squared plus 1, and Picard rank 1. So the Picard rank is clear because, well, this is a 2-vertex quiver, and the Picard rank is 1 less than the number of vertices of the quiver, so Picard rank 1. And this dimension, that's a certain quadratic function in the entries of the dimension. Okay, so in particular, this theorem tells this numerical ample stability is always fulfilled, and that's quite non-trivial. It also tells us that our moduli spaces must be something very, very special. So if you're into Fano varieties, then you know that the classification of Fano 3-folds of Picard rank 1 decomposes into 19 different families. And the only Fano 3-fold I can realize with this method is actually projective space, P3. So out of these 19 very interesting families of Picard rank 1 Fano 3-folds, there's only precisely one space which appears as a quiver moduli space. It's just P3 in most part. Yeah. So in general, for this M Kronecker quiver, the easiest moduli spaces to get are you get all projective spaces, you get all Grassmannians, and then you get some wild beasts, which there are no names for. They are all Fano, and nobody ever asked, but well, here we go. So at least it produces for us arbitrarily high dimensional Fanos of Picard rank 1. Second example is subspace quivers. So m vertices pointing to one central vertex. And the dimension vector we consider is not arbitrary. I can't deal with arbitrary dimension vectors. It's just 1 here, 1 below, and d on the central vertex. So here again are numerical conditions. So d should be between 2 and m minus 1, and d and m. So the entry here and the number of vertices here should be co-prime. And then the moduli space we're looking at is the following moduli space. It's an absolute classic of geometric invariant theory. You take projective space of dimension d minus 1. You take its mth power. So configurations of m points in projective space. You take the stable configurations and you consider them up to the PGLD action, up to the automorphism group of projective space. So that's called the moduli spaces of point configurations, and they are really classical objects. And our theorem says, yes, they are indeed all Fano, and the dimension is d minus 1 times m minus d minus 1 and p covering m. So these are two samples of what kind of examples you can produce. And finally, let me show you the Del Pezzo surfaces. So the previous examples were about large dimensional Fanos. No? So this grows quadratically with D and E. Here the dimension can also be arbitrarily large. But Fanos are only classified in low dimension, and let's start with dimension 2. And the two-dimensional Fanos, so the Fano surfaces, are classically called the Del Pezzo surfaces. And it turns out that we can realize all the Del Pezzo surfaces of degree at least 5 as quiver moduli spaces. And conjecturally, we can only realize these. But I cannot prove this conjecture at the moment. And here it is. So the easiest Del Pezzo surface is P2, and you can realize it from a 3-hour conic quiver. Then you have the Del Pezzo P1 cross P1, which you can realize from this 3-vertex quiver, which I used as a running example. The Hertzebruch surface, the blow up of P2 in 1 point, we can realize from this. Blow up in 2 general points, we can realize like this. Blow up in 3 points, we can realize like this. And up to this point, all the Del Pezzo surfaces are toric. And that's why all the entries in the dimension vector are only 1. But then suddenly, if you blow up P2 in 4 general points, you get a non-toric Del Pezzo, the Del Pezzo of degree 5, and you can realize it as via the 5 subspace quiver. And if you blow up 1 more point, then we cannot realize it as a quiver moduli space. And I don't know why. I have a vague idea, namely, well, this is the last Del Pezzo, the blow up in 4 points, which is infinitesimally rigid, so which does not appear in families. And the next one, blowing up in 5 points, already appears in families. And I would conjecture that only Fanos which are infinitesimally rigid appear as quiver moduli, but I have no idea why it should be true. And well, this is maybe enough for examples, and I'm already over time. So I'll just say thank you for your attention.
Okay, well, thank you very much, Marcus, for this really beautiful talk.
Thank you.
That's wonderful. So I guess everybody clapped and